we are asked to solve for all solutions of these sine equations. One's in degrees, one's in radians. Okay, well, let's go ahead and we have to analyze what these kind of look like so we can have the repeat solution as part of our answer here. So what I like to do is I like to look at the oscillating function for sine. So the oscillating function for sine, I always remember sine starts at the origin and it oscillates and goes back up and down, and it does that on both sides. So I don't want to go too high up there. There we go. All right, so what I like to do when I write this out to lay a foundation is to look at the each of the aspects that are most important here. So where it crosses the x-axis and where it has a maximum or minimum at. So right here is our first one. It has a maximum at pi over 2. And I remember it in radians, and then we can just convert it out. Pi over 2 is 90 degrees if we need it. But for me, I just kind of remember in radians, and then I can convert out if I need to. This is 3 pi over 2, and then this is 2 pi. And then the key here is notice that it starts to repeat itself. I can pick up this function and just lay it right back on here. It has exactly the same look to it. And it's good when we're looking at all solutions is to look at both directions here. So the other direction, there's negative pi over 2. There's negative pi, negative 3 pi over 2. And that's where it repeats at negative 2 pi. So if I pick this up and laid it right over here, it would have that same look also. All right, and it's real important that you kind of get this in your tool belt, because this is our foundation for kind of using a lot of different techniques, especially when it comes to like parent functions and dealing with sine or cosine. Okay, so what this is really saying here is that we have an output of 0.25. So an output of 0.25 is like a y value. So a y value of 0.25 is right about there. So what that means is I have solutions right there and right there, and then I can keep finding more solutions on both sides if I wanted to and kind of keep that repeat process. But when it comes to x, usually we are restricted in our domain here. We like to kind of have a nice little segment that we look at, and then we can have that repeat idea over and over again. So notice that we usually focus on negative pi to pi. So from negative pi to pi is usually what we focus on just in the initial kind of in a parent function way. Okay? So that means these two little dots that I found are the ones that we really want to focus on. And I'm looking for their outputs. I'm looking for the input that gives me that output. So I'm looking for what x gives me the output of 0.25. We can also kind of look at it in another sense too, which is kind of nice. And while I have your attention, we can do that. So here's our unit circle. And this is at 0 or 2 pi. And then I need to just remind myself I'm in degrees, so I'll convert out of that later. So this sine x of 0.25, sine of x is equal to 0.25 is also 1/4. And the sine function is opposite over hypotenuse. So this is the opposite side, that's the hypotenuse side. So if I wanted to kind of analyze it, that would be the x angle here. And I have an opposite side of 1. So that side would be 1. And I have a hypotenuse of 4. Now when I'm doing it this way, I'm not really too worried about the hypotenuse in this instant. The sine is usually the y value. So I'm looking at this 1 right here. And why I did that is these two solutions also show up in this unit circle. So notice I can draw the same triangle that has a 4 for a hypotenuse and a positive 1 for the opposite. So this is exactly the same triangle. That means this has two solutions. That's this solution right here, and then if I travel over and land right there, it has that exact same solution. So the point here is, this is that first, like kind of, I'll call it x1. So this one right here is that x1 idea, and then this one right here is the x2 idea. That's this red that I have shown. That's the x2 idea. All right. So how would I find that? Well, this one you have to use a calculator in. So I'll go ahead and turn on my calculator. I need to be in degree mode. So it's real important, and I've done this a few times already, is that I put my calculator in the mode as soon as I read it in the problem. So as soon as I read that degrees in my problem and I pick up my calculator, the first thing I do is I put it in degree mode. And in degree mode now. Okay, so now that I'm in degree mode, I just want to calculate, and I'll go ahead and go back to this one. I can use the 1/4 if I wanted to, but let's use the 0.25 since we're plugging it in. I'm solving for x, so that's going to be arc sine to both sides. Arc sine to the sine of x. And what you do to one side, you have to do the other. So arc sine to the other side of 0.25. All right, so this are inverse operations. They undo themselves, so I'm just left with x on the left. On the right, I'm typing in my calculator. Arc sine is the same thing as sine inverse. That's what my calculator sees usually. So I type that in. Sine inverse. Sine inverse of 0.25. All right, and the sine inverse of 0.25 in degrees is 14.477, and that goes on forever. Now here's the part where we have to be careful about that repeat idea. So what I'm trying to show you here is that there's a couple different ways of looking at it. First, the way I like the most is I like dealing with the oscillating function personally. So notice that this is going to have that same value right there. When it repeats, right after the kind of the start of the oscillation, bam, there's that answer again. So what that means is we have that 2 pi. This repeats itself every 2 pi. Okay? So this repeats itself plus, and then we would repeat it every 2 pi. And in currently right now they're using n as integers and every 2 pi. So, and then we would just say n is an element of the integers. And integers just means positive and negative regular numbers. So -1, 0, 1, 2, 3, -5. Plugging any of those in, basically you're just repeating every 2 pi, and it doesn't matter which direction you go in. So, this is, that's one of our solutions. That's this x1 solution, so I'll call that x1. That's this, the repeating every time right there. And then, so I took care of that one. That's the x1. And remember, that's pretty easy. It just pops right in the calculator. You have to remember the idea of it oscillating. So how that would look at on this one is that's our solution right there. And then if I go around the circle, bam, I hit it again every 2 pi. I go around the circle 360 degrees or 2 pi. I go around the circle 360 degrees, bam, I land there again. All right, we're in degrees. Oh, come on. So that's not every 2 pi, that's every 360 degrees. So that's kind of the one thing I have to worry about, is that if I remember everything, this is my foundation. If I remember it in terms of pi, I just have to keep reminding myself I'm in terms of degrees for this problem. All right, so that's the first one. And then the next one, that's the key to kind of understand. There's a little bit of arithmetic and logic that we have to use to do this one, is that it's the pi right here, minus this little portion that's kind of getting taken off. And to me it's a little easier to see it on this side. This x1 is the same as that. That degree is x1 right there. This is 180 degrees. So if I take the x1 away from 180 degrees, that gives me that angle. Same idea here. If I have that pi, or 180 degrees, I take that little piece away, it lands me right where I want to be for my x2. So what is x2? x2 is this 14.477, I got still on my calculator, subtracted from the 180 degrees. So 180 degrees minus 14.477 ... These are degrees. I like keeping my symbols going. So 180 subtracted answer is, I get 165.522 ... and this is in degrees. Now the key to remember here is, so that's this angle right here, that's the x2, that's the x2 right there, that's that input, it's that input that gives us that, or that angle right there. So however you want to look at it. And then don't forget, we have that repeat idea. It repeats itself. It repeats itself. This answer right here, every 360 degrees, it lands on it again. So I have that caveat, that extra little bit, that every time I use an integer, -3, -2, -1, 0, 1, 2, 3, going in both directions, for every 360 degrees. So that rotation every time that it lands on it. All right, and those are my two solutions. Yes, and that's all of them that are inside this set. So the key to kind of remember here is that if you have that repeat idea, it helps you kind of link together on each one of these. So if you're talking about this one right here, this solution, which if you see, it would land right there, that's the x2 idea with a -1 right here. So when this is -1, it lands right there. So it hits every solution. And that's the good thing about restricting your domain here, is that if you have kind of a preset way of attacking it, then you have the ability to include all solutions. Okay? That seems pretty good. I was going to go ahead and do another one. It's in terms of radians. You would do exactly the same thing. The only difference is you're going to be down here for your output. Output is -0.25. So that's right here, -0.25. And in between -pi and pi, we would have, it looks like, two solutions would be this one right here and this one right here. So we would be looking at these two solutions. So that's why I really like the oscillating curve, is because it just makes it a little bit easier to see where we're kind of attacking these problems from.